Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to the Fluid Mechanics course. And today we'll be discussing drag and lift force. So we have covered many concepts in fluid mechanics, and we will also see how these concepts are also applied to various further concepts of drag and lift forces. And when we want to discuss about drag and lift force, we will also be able to see that the boundary layer theory that we have discussed, the viscous force or the shear stress that we have discussed, how these are applied to the concepts of drag and lift force. All right. So let us understand what is the drag and lift forces all about. The relative motion between a solid body and the fluid causes the net force to act on a body. So basically when a body moves within the fluid, basically we are talking about the submerged body that is moving within a fluid. Then there is a force that is acting on this body, and that force is nothing but your drag force, or it could be a lift force. So the net force that's acting could be resolved, and we can find out the drag and lift forces. So the resultant force or the force that is acting in directions perpendicular and parallel to the flow, we can resolve and find out the forces that are called drag and lift forces. So if you look at this figure, you have the flow direction, that is the flow coming from this direction, and there is a body which is moving in the forward direction or parallel to the or opposing the flow direction. Okay, so it may so happen that the fluid is static and the body is moving, or it may so happen that the fluid is moving and the body is static. So in both the cases the scenario is different, and what we are looking at is the relative motion or relative flow velocity with respect to the body. So it could be either way, or both of them are moving, and we are trying to find out the relative motion of the fluid with respect to the body, and that flow is going to create a force on the body, and this force is going to be resolved in two components, and one is perpendicular to the flow direction and one is parallel to the flow direction. Okay, so the force that is generated parallel to the flow direction is called drag force, and the force that is generated perpendicular to the flow direction is called the lift force. Okay, so that's what we have written here. The resultant force can be resolved into two components parallel to the flow direction, that is the free stream, and perpendicular to the flow direction, that is again repeating that perpendicular to the flow direction. So it is perpendicular to the flow, not to the body. So that is your lift force. So if we define the drag and lift force, we can write down the force parallel to the direction of motion is known as drag force, and the component normal to the flow direction is called the lift force. All right. Now the drag force, we'll discuss the drag force first, and then we'll go to the lift force. So in case of drag force, we have basically in any force, when we are calculating the force on the body, both shear force and pressure forces are acting, and in case of real fluid, we have to consider both these forces. If the fluid is ideal, then you may say that viscosity is not going to act. If the viscosity is not going to act, then your shear force will not be there. So in case of ideal fluid flow, you might say that okay, there is no shear force, so there will not be any drag force. Okay, but you can still have lift force. But in case of a real fluid flow, both the shear force and the pressure force will act simultaneously on the surface. So the part of the drag force arising out of the viscous action. Okay, so there is a viscosity or the shear stress and the shear force is acting. So the drag that is generated due to the shear is known as the viscous drag, or it is also called the skin friction drag. Okay, or sometimes only friction drag. Okay, so that is one part of the drag, but then there is a pressure force which is acting. So the part of the drag force that is caused due to the pressure force acting on the surface. See, on the body you have pressure acting all sides and everywhere. So there could be a difference in the pressure, and that difference in the pressure is going to create some resistance to the motion, and that resistance or the drag is known as pressure drag or form drag. Why it is form drag? Because depending on the form of the body, shape of the body, the drag or the pressure distribution could vary, and that pressure distribution is going to create the drag. So we call it form drag. Okay, so we have skin friction drag or friction drag and pressure drag. Okay, so the total drag force is going to be a combination of both of these. The total drag force is going to be the drag force due to viscous drag plus form drag. Okay, so what are these and how viscous drag and form drag? Let us have a look at that. If you look at these two figures, you can see this is a simple plate, and the flow or the free stream velocity is approaching this plate from this direction. So now what will happen? There is going to be shear along this plate. We have seen all these things, drag on a flat plate. So there is going to be a drag force on the surface that is mainly due to the shear. Okay, and if we look at the pressure distribution is not going to vary on this side, on the front side and rear side, because this is a thin plate and this will more or less be same. So when you look at, this is mostly due to the skin friction drag. At the same time, if we hold this plate in perpendicular orientation to the flow direction, then we will be able to see that the streamlines what we had smooth, or there was no disturbance or no deviation in the streamlines in the case of the first viscous drag. Here it is completely deviating and the flow is changing. Now if you look at, there is a change in the velocity. You have the free stream velocity here, and because of this change, you see here the free streams are streamlines are closer to each other, so the velocity is higher here, the velocity is higher here, and this part, that's the lee side of this plate, is going to create a kind of void space. So the flow which is going to enter there will have some kind of wake or turbulence and will have a low pressure region. Okay, so this low pressure region is going to create a wake, and you have a high pressure region here, you have a low pressure region here. So that is going to create the amount of drag or resistance in the for the body. Okay, so that force is called as your pressure drag. Okay, now this pressure drag is going to be higher in such scenarios where the body is completely obstructing the flow. Okay, so when a thin flat plate or a disc is held parallel to the free stream, viscous force dominates and pressure drag is going to be zero, or it tends to zero. Similarly, if the plate is held normal to the flow direction, then the drag force is experienced by the body is due to the pressure differentials, and the viscous drag is almost zero. Because here if you look at carefully, the skin friction is going to happen at these two ends, and this is a thin flat plate. So your skin friction is not going to be substantial. Okay, and the drag or the resistance in this direction is not going to be mostly due to the viscous drag. It is going to be mostly due to the pressure drag. All right, so now let us look at different shapes and the contributions. We have already discussed that to some extent. So if your body shape is going to vary, the magnitude of the viscous drag and pressure drags are going to vary. Okay, so if you look at the first statement that is given here, sometimes a fluid moves over a stationary body, and at times body moves through a stationary or quiescent fluid. So I have already discussed that earlier. It is mostly the force is coming due to the relative motion or relative velocity of the fluid with respect to the body. So relative means the body could be moving or the fluid could be moving. So in case of laboratory experiments, we cannot really afford to move the body for a large distance due to the space limitation. So we keep the body static, we blow the fluid and see how it is generating the force on the body. Whereas in real conditions, many times the body might be moving, and it is also possible that you have some kind of bridges and the piers are in the, let us say, water. So the water is moving, the body is static. So all these possible conditions are there. So what we are looking at is the relative motion of the body and the fluid. Okay, so in this case, if we look at velocity of the fluid approaching the body is known as the free stream velocity. Okay, and these bodies, whatever the fluid is going to face or the drag is going to develop on these bodies, they can be classified based on their shape and resistance they experience. So we can classify that as blunt or bluff bodies and streamlined bodies. So when it is blunt body or bluff body, and when it is streamlined body, when you see that contribution of the pressure drag. Okay, here if you see this white patch is showing you the contribution or percentage of pressure drag, and this blue patch is showing you the skin friction drag. So if you have high contribution of pressure drag and low contribution from the skin friction drag, then the body is a bluff body. Okay, and if the skin friction drag and pressure drag are equally contributing, then we call it streamlined body, or it is better if if the skin friction drag is contributing more and pressure drag is contributing less. And why are we talking about that? So let us see, you have this body which is a cylinder or a sphere. Okay, whatever you take it. So what happens, the flow is going to deviate and then it will rejoin, but there will be some kind of wake formation or low pressure region which will be formed on this side. And why it is going to happen, we have already seen in our previous lecture that there is a possibility of flow separation. Okay, so because of that, there could be a low pressure region in this lee side, and that could lead to the pressure drag, and that pressure drag is going to be substantially higher compared to the skin friction drag. Okay, so these wake regions contribute a lot of, or the magnitude of the pressure drag is going to be much higher compared to the skin friction drag. If we can reduce this pressure drag by some means, then our skin friction drag is going to still remain same, let us say, or it might increase with the surface area, but that increase is going to be very less, whereas pressure drag will be reduced substantially, and then we can get a body where the flow is going to be streamlined. And when we talk about streamline, the flow is attached to the body to a maximum length. So if you look at this streamlined body, which is kind of a uh, tail end, you can see that is, so the surface is prepared in or the planned in such a way that the flow is going to attach with the body for a larger distance, and the flow may or may not separate, and if it separates only towards the tail end, and it does not create a large wake region. So it does not create large low pressure region, and it will not lead to large pressure differentials, which will basically ensure that the friction drag or the pressure drag is minimal. So the skin friction drag is only going to contribute, and usually the skin friction drag is not going to be too much. So, or too much compared to the pressure drag. So the body can be called as a streamlined body. All right. So this is a bluff body. Even the plate, when we hold it in the perpendicular direction to the flow, that also is going to behave like a bluff body, whereas these two are known as streamlined body. And if you look at the typical flow and bodies as well as the wake regions, you can see here we are talking about this flat plate where you can see the flow is completely separating here itself, and you have a huge wake region, and this is going to create a huge drag force due to the form. Okay, similarly, if we take a cylinder or sphere, then you have comparatively lower wake region, and if you just flare it up, okay, on the downstream side, then you see this wake has further reduced. Now we have flared it on both sides, so you see the fluid is smoothly transiting and exiting with very less wake region. So the wake region is reduced, that means the pressure drag is reduced. Okay, so our form drag is reduced. So this is the basis how various designs are done. Okay, and we have different shapes. Corresponding to different shapes, we have different drag coefficients also. What is drag coefficient? Basically is a coefficient which is multiplied. We have the formulation for drag. Fd is the drag force, let us say, is half rho u square a is the area multiplied by a drag coefficient cd. So that cd value or the drag coefficient is derived for different types of shapes. So if you see here, these are different shapes. This is a sphere, the drag coefficient is 0.47, whereas for half sphere it is reducing further, it is 0.42, and the arrow mark shows you the direction from which the flow is coming. And you see the frontal shape is going to play a major role, and the flow is going to separate maybe at this edge, okay, and the drag force is going to be less. So cone, for a cone it is going to be 0.5, for a cube it is 1.0, for angled cube it is going to be slightly less, again 0.8. For a long cylinder, this is a cylinder, and for that 0.82. For a short cylinder, you have the drag coefficient which is higher, which is 1.15. Streamlined body it is 0.04, and this streamlined half body it is 0.09. Now you can see just a comparative observation. So this is a streamlined body, and you see it is 0.04. Okay, so that means the total drag, so the drag coefficient is not based on form drag or viscous drag, it is the total drag we are talking about, combination of both, and combination of both is very small for a streamlined body, whereas change in the shape can lead to high drag coefficients, and that will lead to high drag forces. And this is very important because the moment you have some body, and because of the shape of that body, if the drag force is going to be so much, then your force is going to be higher, and you have to design various structures for a higher force, and you need to spend more. So we need to properly plan that. And typically, let us say, I'll give you an example. Here you take a this is, let us say, sphere, but if we take a cylinder, okay, or a circular shape, still the drag coefficient will be more or less similar. And if you compare that with this cube, okay, or a square, so it is somewhere around 1.0, so it's double or more than that. Now if I am putting a pier, a column in the fluid, so there is a flow coming, whether it is air or water, whatever it is. Now that column is going to get some resistance, or it will receive some force due to the fluid motion. Now that force depends on the drag that is going to be generated on this structure due to the structure. Now, if it is a circular pier, then the drag is going to be less, and if it is a square pier, then it is going to be higher. So now you can understand why various places we use circular structures. Okay. All right. So this is an example. There are various applications, various designs based on that, and that we should be able to understand. Now let us look at how we calculate the total drag force. Okay. If you look at the drag force, once we increase or once we try to change the shape of the body, we are changing both. We are changing the skin friction drag as well as the pressure drag. Now, if you have a sphere that we saw just in the previous slides, we have a sphere and that sphere is going to generate some drag, and if we flare it in the downstream and upstream, the drag is changing. So by flaring, we are changing the length. So the surface area is increasing. Once the surface area is increasing, then the induced drag, or which we have been calling as friction drag, due to the friction the drag is induced, that induced drag is going to be higher. Okay, and we have here this plot which shows with different wind speeds or different uh, air velocity. Okay, we have the drag coefficient or total drag that is measured here. So induced drag is going to reduce gradually and the form drag is going to increase, and we will be able to find out the total drag by taking both of these, and there will be a point where the total drag is going to be minimum compared to all other wind speeds. So these are very, very critical in case of various flight operations and uh, movement of uh, vessels or movement of aircrafts, and they need to operate in certain speed so that they can optimize and get a minimum drag so that they can maximize the fuel consumption. So basically with less fuel they can travel more. So these are some calculations which they do and find out which is the optimum speed with which the aircraft or the flight should travel. Okay, so similarly for any shape, if we also change the shape, because of the surface area the induced drag is going to be increasing, or the skin friction drag is going to increase, and then your pressure drag is going to reduce, and we can plot it and find out where we get a optimum drag force, and based on that we can design the shapes. So there are various formulations that are available to find out the drag coefficient. We have already seen some of the formulations based on our previous discussions. Okay, we have already seen that the CD we can write down as 1.328 divided by square root REL. Okay. L is the length over which the flow takes place. So this equation was valid for laminar boundary layer. So similarly, we have seen CD equals to 0.074 divided by square root REL. This is applicable for turbulent boundary layer beginning from the leading edge. Okay, and yeah, beginning from the leading edge means we are assuming that the turbulent boundary layer is from the leading edge itself, but practically we have seen that there will be some distance over which there will be laminar boundary layer and then it becomes turbulent. But here the assumption is the laminar boundary layer is not there, it is the turbulent boundary layer that exists from the leading edge. And in such case, the Reynolds number for which we can apply this formulation is varying from 5 into 10 to the power 5 to 10 to the power 7. Okay, within this range. But if we consider the laminar boundary layer and then we assume that laminar boundary layer exists as well as turbulent boundary layer exists, then we can have this formulation which is 0.074 divided by square root REL minus 1740 divided by REL. So this is applicable again within that same range, but assuming both laminar and turbulent boundary layer does exist. Now, the contribution of laminar boundary layer and the laminar drag is very, very less compared to turbulent boundary layer and drag. So if we consider that negligible influence, the equation can be given like something like this, which is applicable again for 10 to the power 7 and above, okay, up to 10 to the power 9. So the significant, basically why we are revising this, beyond the Reynolds number of 10 to the power 7, the turbulent boundary layer zone is going to be much larger or higher compared to the laminar boundary layer zone. So the contribution of laminar boundary layer is going to be insignificant, and based on that the equation has been modified for Reynolds number greater than 10 to the power 7. And again This is also applicable up to 10 to the power 9. So there are various ranges where the flow characteristics changes and the equations are going to be different, and people have given different empirical relations based on the experiments and studies. So we have these equations which can be used depending on the flow conditions. All right. Okay. Now, having understood this, let us understand there is another important concept, that is boundary layer separation. Okay. So, what is boundary layer separation and why it is important? We have been talking about the flow separating, and there is wake formation, and there is a pressure drag uh, generation, and that is going to contribute immensely. Now, how this happens? This happens with the process of boundary layer separation. So the pressure gradient is the one of the factors that influences the flow immensely. Okay. So the pressure gradient we have already seen earlier. We have talked about negative pressure gradient, positive pressure gradient, or we have also discussed the names, other names. For negative pressure gradient, we said it is a favorable pressure gradient, whereas for positive pressure gradient, we said it's an adverse pressure gradient. So how that also influences the flow and generates or activates the boundary layer separation, that we'll see. So it is easy to see that the shear stress caused by viscosity has a retarding effect upon the flow. We have seen that in the boundary you have the viscous stress, and due to the boundary layer there is a reduction in the flow, and as we go gradually the profile is going to change. Okay. So there is a retarding effect on the flow. This can be overcome if the negative pressure gradient is there. So we have already seen that negative pressure gradient is going to assist the flow. So we call it favorable pressure gradient. And if we have a negative pressure gradient, that will overcome this resistance that we are facing from the surface. Okay. The viscous or the shear stress that is going to be developed due to the viscosity or viscous effect between the fluid and the surface. So we need negative pressure gradient to overcome that. Now it may so happen that this negative pressure gradient is not going to be enough to overcome the viscous or shear stress. Then what will happen? It will come to a standstill, or they will balance each other. And once they balance and still we move forward, then there might be higher resistance compared to the pressure gradient or negative pressure gradient that we have. So then we might have reverse flow. So that is what we are going to discuss, and that is the point where these two forces are equal. The negative pressure gradient, the force due to negative pressure gradient, and the force due to shear stress, they balance each other, they equal each other. The velocity or the motion is going to come to a zero at the boundary. So that point is your point of separation. We'll anyway discuss that. So a negative pressure gradient is termed as favorable pressure gradient, which we have discussed, and the positive pressure gradient is has the opposite effect and is termed as adverse pressure gradient. We have seen that. Okay. So the fluid might find it difficult to negotiate an adverse pressure gradient or a positive pressure gradient, and when it is going to happen, we'll see. It has been also observed that the flow is reversed at the vicinity of the wall under certain conditions which I explained, and the phenomena is termed as separation of boundary layer. Okay. And if you see that the separation takes place due to excessive momentum loss. So basically when there is a resistance, we have already seen there is a momentum which is going to go out because of the reduction in the velocities. Okay. And that loss in the momentum, when it becomes beyond certain limit, you are basically going to have a condition when the flow is going to separate. Okay. So due to the excessive momentum loss near the wall in a boundary layer, trying to move downstream against the increasing pressure, that is the dou p by dou x is equals to 0, sorry, is greater than 0, which is called an adverse pressure gradient. So the boundary layer separation happens due to the excessive momentum loss near the boundary or wall due to the positive pressure gradient. Okay, now let us understand that pictorially. Assume that you have this curved surface or slightly which is uphill first and then it is going downhill. Now when you move uphill, what happens in a surface when you have the uphill? So for the flow, the area available for it for the flow is reducing. So when the area available for the flow is reducing, what happens? The velocity is going to increase, and if the velocity is going to increase, what is going to happen with the pressure? Pressure is going to reduce. So as you move uphill, there is going to be a reduction in the pressure. Now if there is a reduction in the pressure in the downstream, so what will happen? If you take the pressure gradient, you get a positive pressure gradient, and that is your adverse pressure gradient. Okay, now if you do that, then what happens? So due to the curved surface, you will have a change in the velocity, you will have a change in the pressure. Okay, the velocity is going to increase, the pressure is going to reduce. So because of that, what will happen? You will have a favorable pressure gradient up to the point P. Okay, so this tip where the slope is 0, up to that point you will have a favorable pressure gradient, and the pressure gradient is going to beyond the point P, you will have the adverse pressure gradient. Okay, so now the change in this pressure gradient from the point P is going to change the flow conditions near the wall. So now when you have a adverse pressure gradient beyond the point P, now your flow is going to be resisted by the adverse pressure gradient. Okay, in addition you have the stress, that is the shear stress, which is also resisting. So your motion is being resisted in both ways, that is due to the adverse pressure gradient as well as the uh, shear stress. Now there will be a point when the negative pressure gradient will counteract the retarding effect of the shear stress, okay, which is due to the viscosity in the boundary layer. Now in the downstream, the velocity near the wall, it reduces, okay, and the boundary layer thickens. So your boundary layer keeps on increasing and the velocity is going to reduce. All right, a continuous retardation of this velocity, okay, brings the wall shear stress at a point S on the wall to 0. So basically the wall shear stress that is acting due to this force, which is negative uh, or adverse pressure gradient, the total shear stress at this point is going to be 0. So once it is 0, there is no attachment. So because of that, the flow is going to be separated. Okay, so from this point onwards, from the point S, the stress becomes negative and the flow reverses. So first it will be 0 and then it will become negative. So the moment it becomes 0, the separation process starts. So this is why that point is called point of separation. So flow no longer follows the contour of the body. You see, the flow is not attached to the body now, it is now separated. So because of that, we say that the flow has separated, and the point S where the shear stress is 0 is called the point of separation. Okay, and depending on the flow conditions, the recirculating flow dominate and the flow may be reattached to the body. Let us say the surface is kind of a wavy surface, so it might detach at some point, and again because of the curvature the flow may reattach again. Okay, it's all dependent upon the pressure gradient. So we have favorable pressure gradient, then the flow will attach. If we have adverse pressure gradient, at some point when the shear stress is going to be 0, the flow will detach. Okay, the moment the flow detaches, then we have this recirculation which occurs within this zone. When there is a backflow, the flow detaches and there is a shear stress in the opposite direction now, and there is a flow which is reversing, and at some point again it is positive and it's going up. So this area, this zone is going to create a recirculation, okay, and that is going to create some turbulence. So a turbulent flow has more energy and the momentum, more energy and momentum compared to the laminar flow, and this can kill separation and flow may reattach again. So basically what we are telling that we have already discussed about turbulent boundary layers also. So if you have a turbulent flow, the uh, exchange of momentum between different layers are going to be higher. So if you have higher exchange, then the flow velocity is going to still propagate, or it will keep the momentum for larger distance compared to a laminar flow. Okay, so you have more momentum that is close to the boundary and it will keep pushing the flow to be attached to the body and move further. So the separation is going to be delayed in case of turbulent flow, whereas it is going to be very early for laminar flow. So if this flow is laminar, if it separates at this point S, now if the flow becomes turbulent, the separation point come downstream and it may separate further down. Okay, so now this can kill the separation at this point, but it will push downward and the flow may attach for a longer distance. Okay, now the larger the separated region, the larger the pressure drag that we have already seen. So if we can reduce this, the separated region is an enclosed volume and comes to an end where the two flows or the streamlines are going to reattach again. So once we have the flow separation from a body and the flow goes, and there will be certain point where the flow is going to reattach again, or the streamlines which have separated, they will come and reattach again. So this region is nothing but your separated region, and that is what is going to contribute to your pressure drag. Okay, so now due to this, there is some kind of wake formation which is going to happen in the region that we have seen. So we have already understood the boundary layer separation. Now let us understand what happens within this wake region. Okay, so in the wake region, if you look at this body, this is a cylinder, and due to the flow, there is a flow separation, and it generates some wake, and these wakes are in the alternate manner they are generated, and you can see. So these are vortices. These vortices will be generated in alternate manner, and you can see the oscillatory motion. So there is a frequency. So the distance between these two and the time of generation between these two we can take, and we will be able to find out the frequency between this. So wake is the region of flowing trail. Okay, wake is the region of flowing trail, the body, trail of the body, where the effects of the body on the flow velocity are felt. So now this trail is going to be there for certain distance, and again the streamlines are going to move like this and they will reattach at some point. So that zone, okay, we are telling that the velocity is, or the velocity is affected by the presence of the body. Okay, and wake keeps growing behind the body until the fluid regains its velocity back again and the velocity profiles becomes nearly flat or regains its original condition. So now the vortices that are said or generated in the wake region are, as you can see, in the alternate manner. So this pattern is periodic. Okay, and from that we have derived some kind of non-dimensional frequency of the vortices. Okay, so non-dimensional frequency of vortex shading is called as Struhel number, or it is represented by the number, a non-dimensional number, which is Struhel number. So where your Struhel number is equals to fd by u, and where f is nothing but your vortex shading frequency, d is the diameter of the sphere, and u is the free stream velocity. So we have taken all three into account. So you have the shape of the body which is considered, you have the free stream velocity which is considered, and you have the frequency with which this is generated, that is also considered, and we are planning to represent the frequency in a non-dimensional form. Okay, so now this Struhel number which is generated, if we look at various experimental and numerical investigations have been carried out, it's seen that a wide range of Reynolds number gives a Strouhal number of approximately 0.2. If you can see this figure, you see this Reynolds number of 10 to the power 3, okay, is almost 0.2 or even before that, okay, and it goes all the way up to Reynolds number of 10 to the power 5 and more, okay. So a large or wide range of Reynolds number gives you this same Strouhal number. Now why it is important? See, when you have a structure and there is some kind of uh, oscillation or the vortex that is getting generated, it also gives some force on the lateral direction, okay. Now if I have some body like this, and this body or the structure is going to be forced in certain frequency in the lateral direction, this is my flow direction, this is the lateral direction, it keeps on moving due to the wake, and there is a natural frequency of this body. The natural frequency of this body and the frequency that is the vortex is setting and the force is acting, if they match, then what will happen? There will be resonance which will occur, or the frequency or the oscillation is going to increase. So instead of oscillating this much, it will oscillate more. So we want to design the structures in such a way that it is not going to match with the natural, it's not going to match with the vortex setting frequency of the flow conditions, okay, or the flow is designed in such a way in certain cases that it does not match with the structure's natural frequency. So the frequency doesn't match with each other means we can reduce this oscillation and the structure will be stable. Otherwise what will happen? Higher frequency will lead to higher oscillations and the fatigue failures can happen in structures, okay. Anyway, you will understand what is fatigue and all in the courses that you will go when you talk about structures and design of structures and all that, but the fatigue should not happen, and for that we should have the condition, environmental condition proper, and we should be able to design that, okay. So now let us look at some more concepts. So the vibrations generated by the vortices may cause resonance if the frequency of the vortex heading is close to the natural frequency of the body. That is, we have airplanes, we have the suspended breezes, due to the wind load there could be vibrations, and there are tall chimneys, and there are offshore platforms in the ocean which is also encountering the wave forces as well as wind loads, and we provide usually spoilers. So these are some kind of disturbing elements for the flow. So these spoilers are provided around the structure, and basically what they do, they disturb the flow so that the flow is becoming going to become turbulent. And we have already seen, once the flow becomes turbulent, what will happen? The flow will attach with the body for more distance and the separation zone can be reduced. Once the separation is reduced, the wake region is going to be reduced, and because the wake region is reduced, the force is going to be less. So overall the load on the structure can be reduced, okay. This is a typical application. Now let us look at how these concepts are applied, and we are trying to find out drag on different surfaces. So we are going to look at drag on a smooth surface. If you look at drag on a smooth sphere, okay, sorry, drag on a smooth sphere. If you look at the drag on a smooth sphere, you see here it is Reynolds number on the x-axis, and you have the drag coefficient on the y-axis. You see, as the Reynolds number increases, the drag coefficient reduces, okay. At certain point, you see that there is a sudden drop, okay, and this point is nothing but your critical Reynolds number, and that drop happens when the flow ceases to be laminar. So at that point the flow is no more laminar and it becomes turbulent. Suddenly the drag force reduces, okay, because we have seen already with Stokes flow, okay, Stokes law, there is a dominant drag force and it is highly viscous flow. So now in that condition the drag coefficient is going to be very high, and as the Reynolds number increases the drag coefficient is going to reduce, but the moment the flow becomes turbulent, there is a the separation point is going to move downstream. It is not going to separate at the same location. So because of that the drag is going to reduce suddenly, and that reduction you can observe here, and we call that point where it's going to see where the flow is going to flow ceases to be laminar, we call that as critical Reynolds number. Okay, so now the separation of flow occurs just upstream of the midsection for a sphere and a little before the fluid particles are subjected to the pressure hill. So that means if you draw a circle and go from 0 degree to 90 degree and then 180 degree, so your press flow might separate at somewhere around 80 degrees. Okay, just before the midsection. Now the pressure difference between the front and the rear is the main cause for the drag, and that contributes to the form drag. Okay, if we look at a plot and you see here the coefficient of pressure we call it, but it is again representative of the form drag. We are taking the beta as the angle, or you may take it alpha, whatever, it's the angle. Okay, so starting from 0, your 0 is here. Okay, and as you move, the angle is beta now, and this is the free stream velocity direction. With angle beta changing from 0 to 180 degrees, that is to the rear side, we are trying to find how this coefficient of pressure is changing. You can see that it starts from 1 and then it reduces, it comes to some value which is in between -1 to 1.5, and then again it goes back and it becomes 1. So basically that can happen in case of a theoretical analysis, or in theory if we consider that it is the flow is inviscid. In theory we cannot really consider the viscosity. So there, if we analyze, it is a perfect pattern. So everything, the flow regains back its original condition. Okay, the flow is not going to detach, it is going to completely come to the rear end. But whereas if we look at the experimental conditions, you see in experiment the flow, if it is laminar, it is going to detach somewhere around this location which is before the midsection, and the flow is going to separate and there will be a larger wake region. And if it is turbulent, the flow is turbulent, instead of separating here, the flow will be attached to the surface and it will keep moving further downstream, and it will detach somewhere around 130 degrees or 140 degrees, and there will be a much smaller wake region, and that is the advantage, and you will have less drag. Okay. Now let us understand that slow moving particles around the midsection acquire more momentum, and the turbulent boundary layer is able to resist the flow separation for further distance over the sphere, and that's why we are getting a lower wake region. And if you look at a comparison, the drag of on the sphere due to the surface itself, there could be smooth surface, there could be rough surface. Okay, it could be flow, could be laminar or turbulent, but if the surface is smooth or rough, then we can see that for rough surface the separation, the drag force is going to drop beforehand, because the flow, the roughness can generate the turbulent flow, and this drag coefficient you can see can continue up to a larger Reynolds number for a smooth surface, whereas for rough surface it is going to drop somewhere at a lower Reynolds number. Okay, all right. So now similarly we can also see drag on smooth spheres. I will not take much time on this, but we'll quickly move on this. So the drag on a smooth sphere, if you look at, we can first look at the inviscid flow, then we'll go to the viscous flow. So in case of inviscid flow, which I have already discussed, the viscosity is 0 at the stagnation point, and the stagnation point is at this location. Okay, and also at the other end. Okay, the velocity is 0 at the stagnation points located at the front and rear end of the cylinder, and the maximum velocity is going to be v theta, that is somewhere here. Okay, and that is going to be -2u, and it occurs at the theta equals to 90 degrees. The pressure is going to be maximum at upstream stagnation point. So we have already seen that if the velocity is going to be lower, the pressure is going to be higher, that we have seen from the Bernoulli's equation. So your pressure at this location stagnation point is going to be maximum and drops to a minimum at theta equals to 90 degree, where the velocity is maximum. Okay, the net force due to the differential pressures on the circular cylinder is going to be 0, because here it is maximum, again here it is maximum, so the force in these directions are also balanced, so net differential pressure is going to be 0. Similarly, the pressure at this point is maximum and the same pressure is going to be here, and the distribution all around the cylinder is going to be balancing each other, so the net pressure difference is going to be 0. That is for the inviscid flow. But what happens in case of viscous flow is that the pressure difference on the front and rear surface of the cylinder gives rise to significant drag force, because the flow is going to separate at some point. Once the flow separates, it is not going to attach with the body and regain back its own velocity, which was the condition in the upstream. So there is a differential pressure, and that differential pressure is going to give rise to the pressure drag. Okay. Now the experimental data of the turbulent boundary layer follows potential flow better than the laminar boundary layer case. So you can see here, these are different conditions, laminar and turbulent. We have already seen that earlier. So in case of a laminar flow, it separates here, but in case of a turbulent flow, it attaches, the flow is attached to the surface further downstream and it separates at a later stage. Okay. So the total drag experienced by the cylinder drops suddenly, as we have seen earlier, at the critical Reynolds number, and for the cylinder it is 3 into 10 to the power 5. Okay. So if you look at this figure, you will be able to see that the separation, CD, the drag coefficient drops suddenly at some point, which is approximately 3 into 10 to the power 5. Okay. All right. So now let us look at the force, drag force. We have talked about drag, how it is generated, how it is formed, how it's reduced, and how it is going to be more. But now let us look at the calculation of drag force. So when we want to calculate drag force, that is FD, we write it down as half CD rho U square A. And in this, what is your FD is drag force. What is CD? CD is the drag coefficient, which we have already discussed in details. Now rho is the density of the fluid, and U is the flow velocity relative to the object, or in many times it's also called free stream velocity, and area A is the reference area. So this reference area is something which differs slightly the way we think. Okay, and this is the area projected area perpendicular to the flow direction. So drag force FD on any object is proportional to the density of the fluid, proportional to the square of the relative flow speed between the object and the fluid. Okay, and CD is the function of Reynolds number. We have already seen CD is the function of Reynolds number and shape of the object, how the object is. Okay, and A, which is the reference area, is typically defined as the area of the orthogonal projection of the object on a plane perpendicular to the direction of motion. Okay, if I have some object, let us say I have this object and the flow is coming from this direction, the force, drag force, is the orthogonal projection. If I take a cross section, which is the maximum area, that projection area is going to be the area that I should consider to calculate my drag force. In case of a sphere, it is the disc kind of surface, right? So pi d square by 4 is your area, and that should be considered for this kind of calculations of drag force. Okay, in case of in case of compressible flows, the speed of the sound is more relevant, so we don't consider Reynolds number, or we don't give importance to Reynolds number that much. Rather, we give importance to the Mach number, which is used mostly in kind of in the compressible flow conditions, where the uh, aircraft movement is considered, or the propulsion of jets and rockets. So there we need to talk about Mach number. Okay, or CD is more dependent on Mach number, which is a function of Mach number. All right, let us now quickly look at a simple problem which will give you some idea how this drag force is calculated and how its impact on various structures or various applications. Okay, so if you look at this problem statement, it says the drag it says that determine the amount of fuel saved per year as a result of replacing a 15 centimeter diameter circular disc mirror by one with hemispherical back. So you have a mirror on a vehicle. You have a car or you have some bike where there is a mirror attached, and instead of a circular disc kind of mirror where the back is completely flat, if you replace it with a hemispherical back, what is the fuel that you are going to save? So the drag coefficient for a circular disc is given as 1.1 and hemispherical body is given as 0.4. And assume the car is driven 100 kilometer every day at an average speed of 60 kilometer per hour. Assume that the heating value of gasoline is 35,000 kilojoules per liter and the overall efficiency of the engine is 32%. So now here it is moving in the air. So the density of air and gasolines are given, which are 0.8 kg per meter cube and 1.2 kg per meter cube respectively. Now in this case, this is simple. You can always see that the drag coefficients are different. With a disc, for a flat disc it is 1.1, with a hemispherical back it is 0.4. So obviously we can tell that with a flat disc it is going to have more drag or more resistance, it will consume more fuel, and in case of hemispherical back it will consume less fuel. But we wanted to understand how much exactly the impact and what is the fuel saving that happens due to the small change. Just imagine that it's a 15 centimeter diameter, nothing but your small scale. Okay, and with that diameter, if a small change in the design or shape of the body, if we can save some amount, then when we design a larger vehicle and we design it properly, how much energy and fuel can be saved, that will give you some idea. All right, let us look at and solve this problem. If you look at drag force on the body, we have already discussed, it is half rho a v square into cd. Okay, now a is the projected frontal area of the body, which is nothing but pi d square by 4 for the flat mirror. Okay, and if you even the same area is going to be for the hemispherical back because it's the projected area. Pi d square by 4 is going to be the same area that we will be considering, but it's only the drag coefficient which changes. All right, so now if you calculate the fd, your cd is 1.1 pi d square by 4, and this is nothing but your density 1.2 for the air. Okay, for the air density usually you can consider as 1.225 kg per meter cube. Here if you put 1.225 also it's fine. So it is rho multiplied by v square. So velocity is given in 60 kilometer per hour, you have to convert it to meter per second. So that conversion is done here. All right, so by substituting all the values you can get the drag force equals to approximately 3.3 newtons. Okay, now work done to overcome this drag is drag force multiplied by the total distance traveled. So if we calculate that, we will get drag force here, and for the year it is 365, and if we multiply by 100, this is 100 kilometers, so we should be multiplying with another 10 to the power 3, and that will become kilojoule here. So you will have this value which is 120,450 kilojoules per year. Okay, this is the work done or energy. So the energy we have calculated theoretically, but there is a efficiency. Okay, so efficiency if we look at it is 32%. So the energy which is actually required is more, and with a higher energy the efficiency is 32%, which we need for driving the object. So the drag that we have calculated divided by the efficiency is going to give us the actual energy that is required for us. Okay, so the actual energy is 376,406.2 kilojoules per year. Okay, now once we know the actual energy that is required, we know the fuel. Okay, and the fuel, the mass of the fuel that is required is nothing but energy by the heating value, because you heat the fuel and you get the energy. So energy by the heating value is going to be the mass of the fuel that is required. And if we do that, you can see here this energy we have obtained divided by the heating value is the mass, and mass divided by the density of the fuel is going to give you the volume or the quantity, how much uh, fuel you should fill in your tank so that you can overcome this resistance. All right. So we could obtain that approximately 13.44 liters of fuel are required, or gasoline is required per year. Okay. Just to overcome this simple drag force on a 15 centimeter diameter flat plate, okay, or flat mirror. Now if we consider the shape as hemispherical bag, what happens? So now I have already said that the car uses this much gasoline to overcome the mirror. So now the drag force and work done is directly proportional to the drag coefficient. Okay, now we have already seen this. We will not go ahead and recalculate the whole thing. We have already seen if we just change the drag coefficient, the same procedure is going to be followed. So there is no point. So it is the drag coefficient which plays the role. So the ratio, the reduction ratio is nothing but the drag coefficient of the flat plate minus the drag coefficient of the hemispherical back mirror divided by the drag coefficient of the flat plate is going to give you the reduction ratio, which is nothing but 0.636, and that much reduction is going to happen if you just replace this flat mirror with a hemispherical back mirror. Okay, all right, and thus the reduction, the fuel reduction due to the hemispherical back is equals to reduction ratio multiplied by the amount of fuel. And if we do that, we'll be able to see that approximately 8.39 liters, okay, or 8.4 liters of gasoline is reduced just by replacing the back mirror. You may be thinking that per year 8.39 is nothing. For a individual vehicle or individual component, it may be nothing. Just imagine we have millions of vehicles moving on the road, and if the designs are changed, so much of fuel can be saved all over the year, and we can really reduce many things. First of all, we are reducing the fuel consumption, we are saving the money for the public, we are saving the money for government, and we are, most importantly, we are saving some fuel burning, and that is going to save the carbon generation, which is now a hot topic. Okay, so this is a small example how you can apply your concepts for various applications. This is a fundamental mechanics course where we are learning the concepts, but it is important we take the concepts to the real field applications. So you can, from this small application, you can understand how this is going to be useful. Okay, so if we take a whole car, one car shape can completely decide how much fuel is going to be spent. Okay, so depending on that, your fuel consumption and the final expenses and the pollution level, everything is going to be decided. So it needs to be carefully designed. So many designs are done considering all these aspects very carefully.